He's coming to us from the University of Hanoi or, in Vietnam. And he's going to talk to us today about water and Phobos and Deimos and implications for water and tektites.
Okay, so today I'm going to talk about water and Phobos and Deimos, and in particular, I talk about the implication of water in terrestrial tektite for the giant impact origin hypothesis for the moons and Mars. And here's a quick summary, a quick outline. First one is about summary, and then about our study review of water content in tektite, and final is about the implication for water on Phobos and Deimos. Next. In summary, tektite are terrestrial impact ejecta that in some cases have been subject to intense heating and massive loss of water, and they may serve as analog for orbital debris resulting from giant planetary impact. And in this study, we reviewed the water content in Australian in tektite, and which was the highest energy impact tektite, and show that why is generally very low. It's just about 0.01%. It's not zero, and this suggests that even in the giant impact origin hypothesis for Phobos and Deimos, the original material forming the moon might have contained significant water. Okay, so here about terrestrial tektite, and natural glasses derived from impact melting upper crust rock, then ejected into space before formed back and quenching. And tektite presented in many forms: spark form tektite, ablative form, and more known. And here's about the origins and diverse morphologies of tektite. We presented in spheroid, the teardrop, the dumbbell shape. Next. And Australia's in tektite are the tektite were found in Vietnam, in Laos, Cambodia, Southeast Asia, and Australia. And Australian tektite was the largest associated with the largest field in the world. So it will have, so tektite, Australian tektite will have the highest energy tektite. Okay, so now we do a little bit review on water in tektite. In general, tektite contain much less water than volcanic glass, for example, obsidian. And Australian tektite are as the jungle tektite is just about 0.7 million years ago, and they present the highest energy tektite, and it spans the largest field, and they also have the highest water contents among the tektite. And to determine the water contents in tektite, there are two methods. First one is about the manometric methods. It means you heating up the sample and heating up the sample into a vapor, and you collect the gas and measuring the volume of the gas you extracted. So, and from measuring the volume of gas extracted, you can derive the water concentration on tektite. And the second method is the Fourier transform infrared spectrometry. Basically, you're signing up a light beam, infrared light beam, and you receive the absorption spectra. And from the intensity and from the absorption intensity, you can derive the water concentration. And FTR is the most accurate and widely used method. And in this study, we review unpublished FTR water content measurement for Australian Tektites. And here's about the result. So why most other Tektites are very low in water? Australian Tektites having higher in water content. It's about 0.0115%. And even with the most traveled Tektite in Australia, it still have containing significant water. It's not high, it's just about 0.01%, but it still have water. Next. So now let's take a look. Let's take a quick look in more detail about the high energy Australia. Here's a very impressive experiment done in here at NASAM. The artificially ablated tektite have been reproduced with the same surface structure, with a similar thin here about similar thin section, and also the corresponding detail of flange structure. And the experiment demonstrated that the Australian tektite have been the Australian tektite or Australia have been melted 2 times. The second time by the entry back into the Earth's atmosphere. And this demonstrates that the Australian tektite have been the trajectory have experienced exothermic suborbital trajectory, and with the ejected temperature up to 2000 degrees Celsius, and with ejection velocity from 6.5 to 11 kilometers per second. And this velocity is much larger than Mars, the escape velocity from Mars surface. And for the debris forming Phobos and Deimos by giant impact, so surely it have to be the velocity is smaller than escape velocity, so it will be less heated even than Australian tektite. Next. And although there high energy from the Australia, it's still containing water, about 0.01%. Next. So what does it mean for Phobos and Deimos? So as Joanne have talked before, so Phobos and the origin of Phobos and Deimos is still not well conscious. And one of the prevailing hypotheses is Phobos and Deimos are recreated impact ejecta from a giant impact on Mars. And people classically believe that from these origins, the orbital debris from a giant impact are devoid of water. Next. However, the survival of significant water in Australia tektite, even with the highest energy tektite in Australia, have implied that even in the giant impact origin hypothesis for the moon of Mars, the water contents in the original material forming Phobos and Deimos might have contained significant water. And the Australian tektite might provide an approximate estimate for the water contents about 0.01% for the original material forming Phobos and Deimos. Next. And for next step, we need to do more water content measurements of Australian tektite, because now the sample are limited. It's just about 32 measurements. Next. And also with collected more sample and doing more measurement, we need to know also the context of our own sample. It means we need to know about the short location. Also, we need to know more about the curation history, how the sample has been preserved. Next. And also, we need to understand more about the dispersion in water content among Indochina tektite. Next. There are a dispersion in here between the water contents of tektite in Thailand. So even with same place to collect the sample size, even with the same people doing the measurement, there are a dispersion of water measurement in here. And we need to determine that if this dispersion is a real or it's just a measurement in consistency. And next. And the final one, we also need to determine if there is a gradient, a water gradient decrease from Indochina to Australia. Next. Like this, where we have a decrease. So people often argue that the Murnong Tektite were formed in the near impact site, so it has higher in water content than other type of Tektite. So we have a gradient, a decreased gradient from Murnong Tektite in Indochina to Australia. Next. Or this dispersion is just, or there are no dispersions. On the type of Tektite have almost similar, the same in water content. And in conclusion, in the giant impact origin hypothesis for the moon of Mars, so the water content is expected to, in the original material, is expected to be low, but it's not necessarily zero. And Australian Tektite might provide an approximate estimate for the water contents in the original material forming Phobos and Deimos with approximate 0.01 weight%. And however, we need to do more work to understand about the survival and fate of water in the formation of tektites, as well as it would be to understand about the survival and fate of water on the original material of Phobos and Deimos. And thank you.